Welcome back to Inorganic Tutors Institute. In today's lecture, we are basically going to continue with episode 7, right? Where we look at Cartesian products of a set. Cartesian product of a set. Remember, we are still under the big umbrella union and intersection of sets. Union and intersection of sets, right? Now, so far so good. We have been working with 2-set problem, 3-set problem, and we have been combining them, right? Using union, intersection, and Venn diagrams, right? But remember, in all those things that we have been doing, we have been asking questions like, who belongs to which set? Who belongs to which set? Right? 2. We have been asking questions like, who is common to which set? Right? These are the questions that we kept asking in the 2-set and in the 3-set, right? Who belongs to which set? Who is common to which set? Now, in today's lesson, which is the Cartesian product of a set, we are going to switch the question from this particular angle to instead of asking these questions, we will now go and ask that who pairs with who? Who pairs with who? So now the question switched to who pairs with who? Who pairs with who? So this is the question that we are going to ask in the Cartesian product, right? Who pairs with who? Now, remember, in the 2-set and in the 3-set problem, elements are grouped, right? In the 2-set and in the 3-set problem, elements are grouped. But in the Cartesian products, we are going to match the element, right? We are going to match the element to one another, right? So in the 2-set and in the 3-set, we do group elements. We group them. But in here, we are going to match the element, right? So note the differences here again. So rather than us overlapping circles, okay, rather than overlapping circles, we are now going to create ordered pairs, right? We are going to create ordered pairs. Okay, so the idea of combination, all right, the idea of combination is exactly what leads us to today's lesson. All right, the idea of combination is exactly what leads us to today's lesson. So basically, I'm welcoming you to the Cartesian product of set class. Right. So remember, in the previous lesson or in the previous episode, we solved 3-set problem using Venn diagram. We were checking membership, who belongs to which set, who is common to this set, and all that, right? So, but today the direction is going to change. As I said, the direction is going to change. And this leads us to a very important concept called the Cartesian product of a set. So let's look at this definition. All right. So definition. Let's say that A and B be 2 sets, right? A and B be 2 sets. Then we are going to say that the Cartesian products the Cartesian product of A and B written as A cross B, written as A cross B, is the set of all ordered pairs. Is the set of all ordered pairs A comma B, such that A belongs to capital A and small b belongs to capital B, right? So note this definition. Now, look at the key term here. We are going to say that order matters, right? So order matters in here is the key term, right? Order matters. Order matters. So if we are saying that order matters, then it means that we have to think about something like commutativity. So order matters means that the problem we are going to do here, commutativity doesn't hold. So it is non-commutativity. Non-commutativity. So we say that non-commutativity. 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 We are saying that order matters, right? So if order matters, then it is not commutative or it is non-commutative. So let's say that we have element A and B and another element B and A. If you are saying that order matters, then it means that it is not what? Commutative. And if it is not commutative, then that means that A comma B is not equal to B comma A. Right. So this must be noted. Right. A comma B is not equal to B comma A. And that is a very important thing that you have to note in this lesson. Right. A comma B is not equal to B comma A. Now, let me come back to the word ordered pairs, right? So ordered pairs, what does it mean, right? So what is an ordered pair? What is an ordered pair, right? So basically, an ordered pair, let's say that X comma Y has one first component, which is, we are saying that position matters, right? Position matters. Second component, we are saying that position matters. Position matters. So the word ordered pair is an ordered, we say that an ordered pair, let's say X and Y, has first component, and the first component, the position matters, right? And the second component as well, the position matters. Now let's look at something, an example, right? An example. So we say that example 2,5, this is the first element, right? This is the second element. So this is the pair, right? Now, we are saying that this is not commutative because 2,5 is not the same as 5,2. If you look at the definition over here carefully, we are saying that position matters, right? So first component, position matters. Second component, position matters. So if position matters, then we don't have to switch this in place of 5. You don't have to also switch this in place of what? 2. So it means that once you do this, then this is a different thing altogether, and this is also a different thing altogether. So it means that this is not equal to this, and that is what we termed as non-commutativity. Non-commutativity. Now, this is the reason why. This is why A cross B is not equal to B cross A. This is the reason why A cross B is not equal to B cross A, right from here, right? So, we all know that, right? We all know that the Euclidean plane are defined by the set R cross R, right? The Euclidean plane are defined by the set R cross R. And we know that R cross R, right? Or what you can also say that R squared, okay, is equal to P such that P is equal to X, comma Y, such that X, comma Y belongs to R. Now, this R cross R, the first R stands for X and the second R stands for Y, right? Because we are dealing with two dimension, right? So this right here, this is X and this is Y. So this is the first R and this is the second R, right? So realize that we keep getting what? Pairs, right? So if you have, let's say 2 and 5, means that the first element is on the x-axis and the second element is on the y-axis. So that is what the R cross R, or R squared is equal to the set P such that P is equal to X, comma Y, such that X, comma Y belongs to what? R. Now, let's come here and build something, right? Let's try to use similar idea or notation. The Cartesian product of two sets X and T, okay? The Cartesian product of two sets S, let's say S and T, is defined as S cross T, and that is equal to P such that P is equal to S, comma T, right? And S belongs to, small x belongs to capital X and small t belongs to capital T, right? So that is X cross X is basically the set of all ordered pairs, right, of the element S, comma T. So this is telling you that S cross X is the set of all ordered pairs, right, of the element S, comma T, right, of the element S, comma T, with first number or first member of each pair always from the first set, right, with first member of each set always from the first set, right, and the second member always from the second set, right, which is the T, right? So if you have a set like S is equal to A, comma B, and T is equal to B, comma C, then always the first member from the first set will the first member will come from the first set, and it should come from the first set, and the second member should come from the first element from the second set, right? So we have that here. So if you are going to do the pairing, say that S cross T, then we say that we have A comma B, A comma C, B comma B, and B comma C, right? So we have 2 elements here, 2 elements here, we have 4. 2 times 2 give us 4. Now the pairing, first element goes with the first element in the second set. First element from the first set goes with the first element in the second set. Then the first element in the first set goes with the second element in the second set. And you get your first 2. Then you pick the second element in the first set goes with the first element in the second set. The second element in the first set goes with the second element in the first set. And that completes the pairing, right? Now let's look at another example. So example. Let's say that A is equal to 1, 2 and B is equal to X, Y. Right. We want to find A cross B. Right? We want to find A cross B. Right? So for simplicity, we say that so answer or solution A cross B is equal to 1, 2 cross X, Y. Right? So this is what we are going to pair. Now, let me show you some easiest part. Right? Let me show you some easiest part. Now, I want you to fix 1, then pair with all the elements in the second set, right? So fix 1. You fix 1, pair with the first element in the second set. So we have 1, X. You fix 1 again, pair with the next element. Then you have 1, Y. You are done pairing what? The first element. Now fix 2. And you fix 2, you pair with X, you pair with Y. And that completes the pairing. So you fix this, you pair with X, fix it, pair with Y. Then you are done with the first element in the first set. Pick the second element in the first set, fix it, and pair with the second element in the second set, right? So fix 2, pair with X, fix 2, pair with Y, and that completes the pairing. So A cross B, we have 1, X, 1, Y, 2, X, and 2, Y. So that is for this particular example. You see how simple is it? Now, we have been doing this pairing, right? You see, this guy goes to this girl, this guy goes to this girl, and all that. But most of the times, we don't check the order, right? But in mathematics, we respect order, right? In this regard, right? So that is why we are much interested in how you arrange the elements. Now, you can see that the order matters as well. Now, let's reverse the order, right? Let's reverse the order and say that we are going to find B cross A, all right? We are going to find B cross A. That means that we are going to bring the B first. So we have X, Y cross 1, 2, right? So in this regard, we are going to fix X, right? Then we pair with all the elements in set A, right? So we fix x, pair with 1, fix x, pair with 2, right? Then we fix y, pair with 1, then we fix y again, pair with 2, right? And this completes the pairing. So we can see that B cross A, we have x1, x2, y1, and y2. So this is the pairing for B cross A. Now check something. A cross B has its own pairing. Though we have the same number of elements in A cross B and the same number of elements in B cross A, it doesn't necessarily mean that we have the same items in them, right? The quantity is the same, but the elements that are embedded in each cross is not the same. So we can say that from this example, we can clearly see that A cross B is not the same as B cross A, right? We can clearly see that A cross B is not the same as B cross A, and that this example confirms that, right? Now let's look at some characteristics of the Cartesian product. These characteristics, you have to note them very, very well, and it is going to help you a lot. So the next thing is characteristics of Cartesian product of a set. So we have characteristics of Cartesian product of a set, right? Cartesian product of sets, right? Now, I believe you can give some characteristics, right? From the deductions that we have made so far, you can give some characteristics. Not at least you can give some about 2 or 3 characteristics. You can, 1, talk about the order, so order matters. 2, you can talk about the non-commutativity. 3, you can talk about the element are ordered pairs. So all these are characteristics that you can talk about, right? So now let's begin into detail the characteristics, right? So our first characteristics is order matters. Order matters. And this is the most important characteristics that you have to know. Order matters, right? Order matters. Now, the Cartesian product is based on ordered pairs, right? It is based on ordered pairs. So we can see that from our deductions from the beginning, we know that A comma B is not equal to B comma A, right? So we know this deduction, right? From the beginning, that A comma B is not the same as B comma A. Therefore, we can say that A cross B is not the same as B cross A, right? And this is the most important characteristic that you have to know. As I said from the beginning, this is the most important characteristics that you have to know. Although the rest are very, very important as well, but I really, really, really prioritize this. If you fail these characteristics, I don't take the Cartesian product to take it light with you, right? So you have to be careful with this particular characteristics. Order matters. Order matters. Now, the second characteristics is elements are ordered pairs. elements are ordered pairs. So in this regards, we are going to say that every element, let's say of A cross B, every element of A cross B is of the form A comma B, where A belongs to small a belongs to capital A and small b belongs to capital B. Now, note, we know that not that the set A comma B and not AB, right? This thing that I'm talking about, it is not the set A comma B and it is not AB that I'm talking about, right? It is not A comma B, the set A comma B, and it is not AB that I'm talking about. Okay? You have to note this thing very well. It is not that. Now, the third characteristic is the cardinality. The cardinality property. The cardinality property. So with the cardinality property, let's say that if you have the cardinality of A to be M, the cardinality of B to be N, then we can say that the cardinality of A cross B is equal to M cross N, right? That is the cardinality property. If you have the cardinality of A to be M, cardinality of B to be N, then we can say that the cardinality of A cross B is equal to M cross N. And that is very understandable, right? Very, very understandable in here. So that is on the side of the cardinality. This basically holds for finite sets. This holds for finite sets. And now let's go to the fourth characteristic, right? The fourth one is non-commutativity, as I mentioned earlier, right? Non-commutativity. Non-commutativity, right? Let's add a property, non-commutativity property. So with the Cartesian products, Cartesian product is not commutative, right? Cartesian product is not commutative. So that is why we are saying that A cross B is not the same as B cross A, right? That is why we are saying that A cross B is not the same as B cross A. All right? So that is the non-commutativity. Now, refer your mind to matrices, right? You know that matrices, aside addition of matrices, the rest, they are not commutative. Why? Once you change the position of one element to the other, everything scatters, or you have a different result altogether. With the exception of addition of matrices, the rest does not is not commutative, right? And the same idea is applying over here, right? The same idea is applying over here. So you have to take note of that. Now, we are saying that A cross B is not the same as B cross A, even though their cardinality is the same. Even though their cardinality is the same, it doesn't mean that it is equal, right? Even though the cardinality of A cross B is equal to the cardinality of B cross A. But A cross B is not the same as B cross A, even though their cardinality is the same. Remember, when we did A cross B and we did B cross A, we're having the same, the total number of elements in A cross B was the same as the total number of elements in B cross A. But the position of the items in A cross B differs from that of B cross A, right? So that results in the fourth property. Now, the fifth property is the associativity. The associativity. And we know that A cross B, when it comes to the associativity, A cross B cross C is not the same as A cross B cross C, right? So this property also represents the associativity, right? You know that A cross B cross C is not the same as A cross B cross C. Now, the reason is that, or why? You know, if you look at the left-hand side, all right, if you look at the left-hand side of the set, you can see that you have A comma B, right, and comma C. This element is not the same as A comma B comma C. This is not the same, right? So the left-hand side is different from the right-hand side. They are structurally different, right? They are structurally different. You can't tell me that A comma B in a bracket comma C is the same as this. Never, right? So that is why the associativity in here, they are not the same. Okay, now let's look at the set property or the set characteristics. So the set characteristic is the Cartesian product with itself. The Cartesian product with itself. So with the Cartesian product with itself, let's put out a claim, right? So for any set, right? So we are going to say that for any set A, we can say that A cross A is equal to A1, A2, right? Such that A1, A2 belongs to A, right? We placed a claim and we are saying that A1, A2 such that A1, A2 belongs to what? A. Now, you can say that this is A1, this is A2. They are all A's and A is an A, whether it is A2 or A1 or whatever it is an A. And they all belong to what? A. So that is what we are talking about, Cartesian product with itself. If you cross A to itself, you result in what? A itself, right? It's like multiplying yourself by yourself. You get yourself back. And that is the same idea we are applying over here. Now, we can see that this forms all possible ordered pairs. All possible ordered pairs from the same set. All possible ordered pairs from the same set, right? So this is what is forming that all possible ordered pairs from the same set. Now, the seventh property or the seventh characteristic is the seventh characteristic is empty set property. Empty set property. Now, this is one of the interesting property that you have to know, right? So if we are saying that let's say either set is what? Empty, then we can say that A cross an empty set produces what? An empty set. Now, this is an empty duster, right? And we cross it with another, with a set, right? So this is a set which contains element, and this is what? An empty set. When you cross it with this guy, because this one is empty, you result in an empty set, right? Because it's like multiplying 0 by a huge number. You result in what? 0. So it doesn't matter the quantity of the element you are pairing with. Once it is empty, it results in an empty set. So we say that if either set is empty, then we say that A cross empty set produces an empty set, right? And when you cross an empty set with a set, you produces what? An empty set as well. So that is the illustration that I did. If this is empty, this is a set, right? Now, you cross these two, you produce an empty set. Yet, if this is empty, right, and this is also the set, and you cross these two, it becomes empty. Once one of the element is empty, the result will be empty set. That is so beautiful, right? So beautiful and interesting. Now, we are going to do something very interesting right here. Okay, so once we understand this, then we should know that this is basically telling us that no element, no pairs, right? If we have no element, then we can't do any pair, right? So we say that no element implies that we have no pairs, right? No element implies that we have no pairs. Now let's look at the eighth property. The eighth property. So the eighth property is the subset property. The subset property, right? So if, let's say we have an element A1 that is a subset of an element A2, and we have an element B1 that is a subset of an element B2, then we can say that A1 cross B1 produces or is a subset of A2 cross B2. All right. If A1 is a subset of A2 and B1 is a subset of B2, then we can actually say that when we cross A1 and B1, it should be a subset of what? A2 cross B2. And this makes sense, right? This makes sense a lot, right? If we are crossing this with this, that means that it will be a subset of we crossing this with this, right? That is perfectly good for the subset property, right? That is perfectly good for the subset property. Now let's look at the ninth property, which is the distributive property over union. The distributive property over union. So with the distributive property over union, it is very interesting from this part onwards, right? If let's say you have A cross B union C, then we can basically say that when you cross this, right, when you expand this bracket, you're going to have A cross B in a bracket union A cross C, right? You pair this with this, right? And that becomes A cross B, right? And then you pair this with that, and that becomes A cross C. But remember, there is an item between these two, and that is the union in there. And so, that union is what? Addition, right? So, and it represents or, right? So, this A cross B or A cross C, and that represents A cross into brackets B union C. Now, let's look at the other way round, right? So we can similarly say that. So that is for the first part, right? So similarly, you can say that. So similarly, we can say that A union B cross C is the same as A cross C union B cross C. And this also makes sense. We spread this to that, and we have this. We spread this to that, and we have that. So similar way we did this, the same way in here, right? And this is this is very, very common in proofs writing. This distributive property over union is very common in proof writing. So take note of this property as well. It's very, very common in proof writing. All right. Now let's look at the 10th property. Let's look at the 10th property. So the 10th property is the non-distributive over intersection. Non-distributive over intersection, right? Now, we know that A cross B intersection C is the same as A cross B intersection A cross C, right? So if you have the intersection as well, you spread this to that and you have this, you spread this to that and you have this. So that is non-distributive over intersection, right? The non-distributive over intersection. Now, this property, it works. This property, this does work. This does work, right? Unlike what is coming up very soon, unlike for the difference, unlike for difference, right? So this, it does work, right? It does work, but it is not like the difference property. And I agree with that completely, right? Because if, let's say you have two elements, 2 and 3, all right? And you're saying that 2 minus 3 is the same as 3 minus 2, then there is something wrong with you, right? If you have this element, right? 2 and 3, and you're saying that 2 minus 3 is the same as 3 minus 2, then there is something wrong with you. Are you okay? So the difference property in here doesn't work like the intersection, right? So the difference property doesn't work. All right. So the 11th property is the difference property. Difference property. And so with the difference property, we have A cross into bracket B minus C is the same as A cross B minus A cross C. But when you have A minus B, all right, cross C, this is not the same as A cross C minus B cross C, right? If you have A cross into bracket B minus C, we can perfectly say that it's the same as A cross B minus A cross C. Just like spreading the A across the bracket, right? But if you have A minus B cross C, you cannot say that A cross B is the same as A cross B minus B cross C. It doesn't sound well, right? Okay, so that is the 11th property. Now let's look at the 12th property, which is the finite versus infinite set, right? The finite versus infinite set. So let's say that if both sets are finite, then the product is also finite, right? You have to know that if both sets are finite, then the resulting product will also be what? Finite. So note that if both are finite, or if both are finite sets, then the product will be what? Finite. Right. Now, if you have, let's say, at least one of the sets, right? If one is infinite, then the result will be what? Infinite, right? If at least one is infinite, then the result, the product, is infinite. The product is infinite. So if at least one is infinite, then the product is what? Infinite as well. That is the 12th property, right? The 13th property, that is the foundations for relations. The foundations for relations, right? So let's put out a claim, right? So let's say that any subset, right? Yes, we are going to use any subset in here. Any subset R that is any subset R, A cross B, is called a relation form. A relation form that is A to B. All right, that is A to B, and this is why Cartesian product. This is why Cartesian product is fundamental. This is why Cartesian product is fundamental. All right. R is a subset of A cross B, and is called a relation, right? It is called a relation form that is A to B, and this is why the Cartesian product is a fundamental in sets, right? That is why the Cartesian product is fundamental. Great. That is the 13th property, right? The 13th property. So we are going to look at the last property, or the last characteristic, then we start solving problems, right? So the 14th property is the coordinate geometry interpretation. The coordinate geometry interpretation. So let's say that A, we have R cross R. So this is X, the Cartesian plane. This is X and this is what? Y. So you can say that this result was R squared, right? Now, this represents all points in the Cartesian plane, right? All points in the Cartesian plane. 2. Each ordered pair, let's say X and Y, is a point. Each ordered pair, let's say S and Y, is a point. So let's say that you have 2 and 3. This is a pair, ordered pair, right? And it is a point. So ordered pair means that this is strictly for X, this is strictly for Y. So on X, we have 2, on Y, we have 3. So this is the points, right? Okay. Now, let's take example, right? We are going to take examples. Now, we have learned all the properties, the 14 properties, though some are minor, right? But it is very important that we know them, right? It is very important that we know them. Now, example 1. Example 1. Let's prove that A cross B is equal to B cross A, right? If and only if either A is equal to B or at least 1 is empty. Either A is equal to B or at least 1 is empty. We are going to prove that A cross B is equal to B cross A. But we know that in the Cartesian product, A cross B is not equal to what? B cross A. But we have been given a condition. If not this condition, this doesn't hold, right? So let's look at it. So we say that let A equals B, right? So this implies that A cross B will be equal to what? B squared, right? Or A cross B will be equal to what? A squared, right? I believe we are saying that A is equal to B. So it means that if A is equal to B, then we can say that A is equal to A. Or we can say that B is equal to B. That is why we are saying that A cross B is equal to B squared. Or A cross B is equal to what? A squared. Because we can substitute B with A, and we can substitute A with what? B, right? And that results in these formulations. Now, on the other hand, we say that A is an empty set or B is an empty set, right? Then this implies that A cross B is an empty set, right? Or B cross A is also an empty set, right? So based on this deduction, we can therefore say that A cross B is equal to B cross A. This is very, very simple, right? Very, very simple. We just use the conditions that we were given to do this proof. All right. Now, we are done with this particular proof, right? Let's look at, so this is example 3, right? And this example falls under Cartesian product and union, right? So we want to find A cross B union C, right? So remember, basic mathematics still applies here. Bracket first. So you find B union C, right? So B union C, you're going to have A, comma B, comma C, right? You combine these two elements. So the summation of these two elements, you have A, comma B, comma C. Now, you're going to pair this with that. So A cross B union C, right? You're going to have 1, comma 2 cross A, comma B, comma C, right? So the same pairing again, we say that you fix 1, then you pair with all the elements in A in this particular one, right? So you fix 1, you pair all the elements in what? The B. So we have 1, comma A, 1, comma B, we have 1, comma C, and that ends the pairing for what? 1. Then you fix 2. Fix 2, then you pair with all the elements in what? The second set. So you have 2, comma A, you have 2, comma B, and you have 2, comma C. Right? So we have 1, 2, 3, 1, 2, 3, and that's 6 elements. 2 elements here, 3 elements here, and that is what? 2 times 3 is 6. Right? 2 times 3 is 6, and that is what we have here. So the element that we had from A cross B union C is 1, comma A, 1, comma B, 1, comma C, 2, comma A, 2, comma B, and 2, comma C. And that is the third example. The fourth example is example 4. Let's say that we have A equals 1, 2, 3, 4, right? And B is equal to X, comma Y. And C is equal to P, comma Q. Right. We want to know the total number or the total element in the cardinality of A cross B cross C. So first question, or I, what is the total element? What is the total element in A cross B cross C? Right? What is the total element in A cross B cross C? Right? So this is where we have to, like I did here, 2 times 3, and that's it. So we are interested in the total number of elements in A cross B cross C. So A cross B cross C, the cardinality will be equal to 1, 2, 3, 4. So we have 4 times 1, 1, 2, right? Times 1, 2, right? So that is equal to 4 times 2, 8. 8 times 2, 16. So the total number of elements in the cardinality of A cross B cross C is 16. You just have to count the number of elements here, note it down, count the number of elements here, note it down, count the number of elements here, note it down. When you're done, multiply everything. Then you count the total number of what? Element in those 3 sets. So that is for question number 4. Right? Let's look at example number 5. So with question number 5, we are going to find, or we have been given this preamble, right? Let's say we have a set A, B, and C, and we have been defined, those sets have been defined in each of the following, right? So A is equal to X1, S2, S3, B is equal to Y1, Y2, C is equal to Z1, Z2 for A, right? And B A is equal to x1, x2, B, y1, y2, y3, and C. The question C, A is equal to x1, x2, B is equal to y1, y2, and C, we have z1, z2, z3. Now, we want to find the Cartesian product in each case, right? So, when it comes to the A, we want to find A cross B cross C. So, AI, BII. So, this is BII. This is CIII. So, we have CII. So, with AI, we want to find A cross B cross C. With BII, we want to find B, A cross B. And with CIII, we want to find A cross B cross C. So what I'll do here is that I'll do AI, which is the first set, then I'll leave BII with you for you to try. And I'll give additional quick practice problems so that you add it to it. You do it, you leave your answer at the comment section. Okay, so I'm going to leave question number 5 to you. Give it a try. Leave your answers at the comment section, right? Now, another quick practice problem that I want to leave with you. Question 1. Let P equals the set X and Y. P equals the set S and Y. Q equals the set 1, 2, and 3. Now, I want you to find I. P cross Q, I, Q cross P, and I want you to compare the two sets, right? Question 2. Let A equals the set 1 and 2. B equals A, B, C. Now, I need you to find I, A cross B, B cross A. And then I want you to state the number of elements in each case, right? Question 3. Let A equals the set 1 and 2. B equals the set A, B, and C equals the set B, C. Now the question is, find B intersection C and find A cross B intersection C, right? So this is the problem. Work out the question number 5, example number 5, then do the quick practice problem. Leave your answers at the comment section. Right? See you in the next video. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye-bye.